Hello, in this video I'm going to be giving you a bit of background as to where the determinant of a matrix comes from and maybe a bit more as to what it actually does and what it means geometrically. If you're just interested in how to find and calculate the determinants, then I will link my videos on that in the description, as well as my playlist on matrices, so you can just go and watch that if you're more interested in just how to do the calculations. If this video is useful, then please do like and subscribe and go over to my channel for tons more maths tutorials. So let's see where the determinant comes from and let's see what it actually means, and to do this we're going to look at it geometrically. So you can see below I've defined a unit square and I've outlined it by marking each of the vertices like so. And what we're going to do is we're going to transform this unit square by a transformation matrix A. Now we haven't actually looked at how we can transform a shape by a matrix, we'll look at that later, but it's actually really simple. We just multiply each of the vertices of our shape by the transformation matrix, and that output is going to give us each of the new vertices under the transformation. So let's do it in this example here. So I'm going to take my transformation matrix 3, 2, 1, 4, and I'm going to multiply it by a matrix where the columns are the vertices of the shape. So for example, the origin. So let's see what happens to the origin under the transformation. Well, you can see we get the origin back out. So we can say, well, under the transformation matrix A, the origin remains fixed. It doesn't move. Now we can do this for the point 1, 0, the point 1, 1 and so on, okay, individually, but this might take a while. So what I'm going to do is just do it as one big matrix where each column is the vertex of each point. So we've got the origin, then the point 1, 0, then the point 1, 1, and finally the point 0, 1. So let's see what happens under this transformation. Well, like we said, the origin's fixed. The point 1, 0 is going to turn into the point 3, 1. The point 1, 1 is going to turn into the point 5, 5. And the point 0, 1 is going to turn into the point 2, 4. And you can multiply that and see how that works. So let's get rid of this so I have some more space. Now, as we said, the columns of this matrix represent the new vertices under the transformation. So let's plot these onto our graph. So the origin is fixed. We've then got the point 3, 1. So let me go across 3 and up 1. So we've got the point 3, 1. We've then got the point 5, 5. So let me mark that on. Let's go up 1, 2, 3, 4, 5. We've got the point here. Let me mark it on the axis. You'll see why I'm doing this in a second. And the point 2, 4. So 2 and up 1, 2, 3, 4. The point 2, 4. So let's see what has happened to our unit square under this transformation. Well, we can see we've ended up with a parallelogram. And this will always be the case, okay? Whenever you're transforming the unit square by a given transformation matrix, you're always going to end up with a parallelogram. Now, the determinant, okay, is going to tell us the area of this transformed unit square, okay? And we're going to see why in a second. But more generally, if we take any shape we like, it doesn't have to be the unit square. If we take any shape and we transform it by a given matrix, the determinant of that matrix, okay, will give us the scale factor for which the area has been transformed by it. So let's check how it works, and I'll show you how to calculate the determinant as well. So how could we find the area of this parallelogram? Because we don't have the base or the height. Well, what we could do is we could say, well, look, this big shape here, this big square, well, the whole shape is encased in that, and that has an area of 25, doesn't it? Because it's 5 times 5. So the area is going to be 25. Subtract all of this outside region, because that's just going to leave us with our parallelogram. So let's find how we could take away that outside area, and there are a couple of ways we could do it. We could split it up like this. So we've got now a triangle that we can take away. Well, the base of the triangle is 3 and the height is 1. So I'm taking away a half times by the base times by the height. I'm then going to subtract, well, I could split it up into this rectangle and another triangle. But to make it a bit faster, what I'm actually going to do is keep this as a trapezium. You can see I've got my two parallel sides here and here. One of the sides of this trapezium, the parallel one, has a height of 1. The other one has a height of 5. And it's going to have a height here of 2. So I'm going to multiply it by 2 and then divide it by 2. So that's this bit done. Let's then find the area of this triangle. Well, it's going to be minus a half times the base. I'll take this to here to be the base. So that's 4. Multiplied by the height. Well, the height is going to be 2. And finally, you can see I have another trapezium here. I'm going to take away, well, one of the parallel sides has a length of 2. The other one has a length of 5. And it's got a height of 1. And I'm dividing that by 2. Okay, let me put this all into my calculator and we'll see what we get as the output. And so my calculator has output 10. And so the area, okay, of this parallelogram is 10. And we'll look at why this formula works in a second, but the formula to find the determinant is we take the leading diagonals, multiply them together, and then we subtract the other diagonal from that. So the determinant of A, which we can write as the det of A, okay, is equal to 3 times 4, subtract 2 times 1. And so we're going to get 12 take away 2, which is 10 as well. And so like we said, this determinant tells us the area of the transformed unit square under the transformation matrix A, or more generally, the scale factor for which an area of a shape has been transformed. Now, why do we do the leading diagonals, take away the other diagonal? Well, let's take a look at a more generic case. So here I've got some generic transformation matrix ACBD, and what we're going to do is do the same thing again. I'm going to multiply each vertex of the unit square by this matrix. So I'm going to multiply it by, let's write it out, the origin first, so 0, 0, 1, 0, 1, 1, and the point 0, 1. So let's see what happens to each of these points under the transformation. Well, the origin remains fixed. We're then going to get some new point, A, B, like so. Then we're going to get A plus C, B plus D, and finally we're going to get the point with the coordinates C, D, like so. So let's plot each of these points, and I know sort of what it's going to look like. It's going to form a parallelogram, isn't it? So I've got the origin. Let's then say the point AB is, I don't know, over here somewhere. So this point here is A, and this bit over here is going to be B. Let's do the point A plus C, B plus D. Well, let's say I'm sort of estimating it. It's not going to be perfect. It's over here. So this point here is A plus C, and this point over here is B plus D. And finally, let's do the last point, CD. Well, I don't know what that's going to be exactly. Let's sort of estimate. It's not going to be perfect. Say it's about there. So this is going to have the coordinates C and D, like so. There we go. Let's then draw this parallelogram because it's going to form one. It's not awful. There we go. Sort of, you get the point. This is our parallelogram. Okay. How can we find the area of this parallelogram? Well, we're going to do it the same way as we did it above. But first, just to make it really easy, I'm going to find all of the points I'm interested, or the lengths I'm interested in, or at least most of them. So we know that from here to here, okay, well, we start at A and I end up at A plus C. So this distance here must be C, okay. Let's then do another one. Let's do, well, here I'm starting at D and I'm going up until I get to B plus D. So this distance here must be B, okay? We might need some more, but just so we get a sort of an idea, this is going to be really useful for later on. So let's first outline the whole sort of square shape, or the big rectangle that we've got. So we're going to have B plus D multiplied by, let me remove that just because I can't quite read it, A plus C. So this is going to be the area of our new parallelogram. So first thing I'm going to do is subtract the area of this right angled triangle. So I don't want equals, I want subtract. So I'm going to subtract that, so that's a half times by the base times by the height. And just to keep it clear, I'm going to write it in sort of alphabetical order as I go. So half times by the base times by the height. There we go, that's this area done. Let's split this up into a rectangle, so it's going to have a base of C and a height of B, so minus BC. Let's then take away the area of the right angled triangle above it, so minus a half times, well, the base is C. Now what's this height? We haven't found this one out, let's do it. So this is B, and we're going all the way up until we get to B plus D, so this must have a height of D. So we're going to be subtracting half C multiplied by D. Okay, let's do the same on the other side. So here we're going to have a right angled triangle, so minus a half times the base. Well, the base length is D, and it's going to have a height of C, so minus CD. And then let's split this up. We've got another rectangle here, so this is going to have a base of C and a height of B, so minus BC. And finally, we've got one more right angled triangle, and again, we need to work out one of the lengths. So here we're at C, and we're going all the way up to A plus C, so this must have a height or length of A there. I'm talking about this distance. Hopefully this is sort of clear. So we're subtracting a half times by, say, the base, which is going to be B, or A, do A first, A, and then B, like this. So let's expand the brackets and see if it simplifies. So we're going to get BA, so we write that as AB, plus BC, plus AD, plus CD, minus, well, let's see if any of these terms simplify at all. We've got minus 1/2 AB here, minus 1/2 AB here. So that makes minus AB, and you'll notice actually that will cancel out with this AB here. Perfect. We've also got minus 1/2 CD here, minus 1/2 CD here, so that's just minus CD. Well, that's going to cancel out with this CD, so we're just left with minus BC minus BC. Okay, and we'll notice again that there's a BC here that's going to cancel out with this one, and so we get left with the area of our parallelogram is AD minus BC. And so this is where our formula for the determinant comes from. So if we have a 2 by 2 matrix, okay, like we defined up here, so A, B, C, D, let's call this matrix A, then the determinant of matrix A is going to be equal to AD minus BC. So this is a formula that we can use. Now, when it comes to 3 by 3 matrices, okay, I'll define the formula for that in the next video. But the idea in terms of scale factors remains the same. So if we take a unit cube and we transform it by some 3 by 3 matrix B, then what this is going to do is transform this unit cube into what we call a parallelepiped, which is a shape where each side of it, all 6 sides, are made up of parallelograms. And so what this tells us is the absolute value of the determinant of a 3 by 3 matrix is going to be the volume of our parallelepiped. And for a generic 3D shape, the determinant is going to give us the volume of the scale factor for the 3D transformation. So hopefully this video was useful. If it was, please like and subscribe. I'll link my video playlist on matrices below, and go over to my channel for tons more A-level maths and further maths tutorials. Thanks for watching.